So this question reads, consider two charged spheres of equal size carrying a charge of 6 coulombs and a negative 4 coulombs, respectively. The spheres are brought in contact with one another for a time sufficient to allow them to reach an equilibrium charge. They are then separated. What is the final charge of each sphere? They are then separated. What is the final charge of each sphere? Okay, so this question basically is about charge redistribution by conduction because you are bringing these two spheres together. You are bringing them into contact with each other, which means there will be charge redistribution. And since it's taken place by contact with each other, we call it charge redistribution by conduction. So when these two spheres are touching each other, the charges are going to be freely moving from one sphere to another until they reach what we call what? What we call an equilibrium. Or in full, we call it an electrostatic equilibrium. And once equilibrium is reached, I'm sure you know, you now understand what happens when any kind of reaction reaches equilibrium. We talked about thermal equilibrium when we were talking about thermophysics, and I'm sure you also talked about chemical equilibrium in chemistry when talking about different chemical reactions. So when equilibrium is reached, electrostatic equilibrium in this particular case, you're going to notice that both spheres are going to end up with the same electric potential. And in this particular case, where they've told us to say the spheres are of equal size, where is it? They've told us to say the spheres are of equal magnitude here. The spheres are of equal magnitude. What does that mean? That means they are also going to share the charge equally. The charge distribution at the end is going to be equal. They will share the charge equally. That's what you're supposed to understand in this particular question. So which principle are we going to use? We're going to apply what we call the conservation of charge, which means the total charge before contact should be equal to the total charge after contact. So I can write this down to say Q total should be equal to what? Should be equal to the charge 1 plus the charge 2. The total charge after contact should be equal to the total charge after contact. Then after we do this, what are we going to do? We're going to say the final charge per sphere, charge per sphere, finally, per sphere rather, sphere will be equal to what? It will be equal to the total charge divided by 2. Since we have two spheres that are of equal magnitude, that is the principle that we are going to use, or these are the principles that we are going to use. So first things first, let's add the initial charges to find the total charge. And which initial charges do we have? We have positive 6 coulomb and the negative 4 coulombs. So I'm going to say my total charge, which is Q total, will be equal to what? It will be equal to the positive 6 coulombs plus the negative 4 coulombs, like this. And what is going to be my final answer? If I add these two, positive 6 plus negative 4, this is basically going to give us a positive 2 coulombs. So this is going to be our total charge in this particular case. And since they've told us to say the charges are of equal magnitude, that means we're going to go ahead and apply this principle to say the charge per sphere, then the Q per sphere will be equal to the total charge, which in this particular case is 2 coulombs, divided by the number of spheres, which in this particular case is 2. That means the charge per sphere will be equal to what? It will be equal to positive 1 coulomb. So each of the spheres is going to carry positive 1 coulombs. So the things that you're supposed to really take note of when you find such a question is first, check the size of the spheres. Check if the spheres are identical. That means then that is going to tell you how you're going to divide the total charge at the end of the day. Then also don't forget the signs when adding the charges. If it's negative, consider it as negative. If it's positive, consider it as positive. You understand, right? So if the spheres are of different sizes, this is one point that I also want to make. If the spheres are of different sizes, that means even the charges themselves would not be shared equally. They are going to depend on the radius of this particular of each particular sphere. So once the sizes of the spheres are different, you are going to include the radius of the spheres in your equations to calculate, because they are not of the similar magnitude. They are different. So even the sharing of the charges is going to be what? Is going to be different. Are we together there? So once you have a different, let me just write it here. So I'll say once you have a different charge size, I'll write it here or not here. All right, like that. Okay. So once the charges now, or the spheres rather, not the charges, once the spheres of different sizes, what do? We know to say, in order for us to reach equilibrium, what does that mean? That means V1, which is the voltage, should be equal to what? Should be equal to the voltage 2. And how do we calculate the potential of conducting spheres? We say V is equal to K multiplied by the charge divided by the R, like that. This R that we've written here is the radius. The Q that we have here is the charge, and K is a constant. K is the constant. So since potentials are always equal, here we said V1 is equal to V2. Since the potentials are always equal in this particular case, what does that mean? That means the charge Q is directly proportional to what? Is directly proportional to the radius. So the charges divide in proportion to their radius and not equal. We've said it's directly proportional and not equal. Which means even the charges themselves, they're going to divide proportionally to their radius, but not equally. What does that mean? That means if I want to put this into an equation, or I'm coming up with an equation from this, I'm going to say Q1. I'm sure we've already looked at such equations when looking at gas laws. Q1 over Q2 should be equal to what? Should be equal to R1 over R2, like this. This is what we have. So in a case where we've been given different radius, you're just going to start plugging them into this particular formula in order for you to be able to do what? To be able to get the charge per sphere. That is in a case where they've given you spheres that are of different magnitude. So if maybe say, let's say for example, there is one sphere which had the radius of 2 meters or 2 centimeters, and another one which had let's say this is a ratio of the radius. What are you going to say? In order for you to be able to calculate your Q1, let's say your Q for the first charge, what are you going to do? What are you going to do? We're just going to add these ratios. You're going to understand to say the first sphere has a radius which is 2, and then the second sphere has a radius which is 1. So what is the total of the radius? The total is 3. 2 plus 1, that is 3. So in order for us to find the radius of, the charge of the first sphere, we'll say this will be equal to what? Since the first sphere has a radius of 2 over the total radius, which is 3, we'll multiply this by the total charge that we found here, which is 2 coulombs. Then I'll say multiplied by 2. And I'll do the same to find the charge on the second sphere. The second sphere has a radius which is equal to 1 over the total, which is 3, multiplied by the total charge, which is 2. And that is how we get the charge per sphere in a case where we've been given different spheres that are different in size with different radii, or with two different values of radius. Any question here? Any question here? Okay, so if there's no question, that is all about this particular question.